I have no idea why they removed that video. That for some strange reason, I don't know. That says I might have violated copyright. I don't know what copyright I violated because it's only me. Maybe I have some music in background. I don't know. In either case, we are back again here. So you should probably just subscribe to my channel so you don't have to worry about this kind of things happening. Because if they drop my video for some reason, the stream, you can just simply refresh the page and you're going to be back again. So we're going to be doing this test of significance of correlation, which is our lecture number 12, in about 5-6 minutes. And you can read the lecture. Is one of the lectures is added to the Blackboard in that lecture and tests menu option. And so I'm gonna wait for a little bit until I get a few more people here joining. Yeah. Yeah. I don't know what's going on. Add some more here. It's gonna work out. YouTube kicked me out. YouTube kicked me out. It says that I'm violating copyright. I'm doing my own lecture, and they just knocked my stream out for some reason. I don't say now you have to complain. I don't have time to complain, but I just need to have the stream set to make another one. Gee, it's not working as smooth as I thought. Although last time.
Maybe you need to record it at 0:09. Nobody.
Yeah, like when we're talking, you're going to be sleeping. You're going to complain about it. We'll do something. I'm still waiting. 3:30. Yeah. Talk about it. Let's see what I have here. Okay, we might as well start. I have maybe a minute or less to go. So what we're going to be talking today is about the significance of correlation. How do you decide that you have a correlation that is significant? All right. So that is the story we had from the last time. And the last time we said that when you get something about correlation coefficient that is going to be close to 1 or -1, that you can start thinking maybe you have a correlation between X and Y. There might be a relation between X and Y that is of some importance. But because the sample size also matters, and when you have a sample size that's very small, then you might have an indication of correlation just coincidentally. And it might not be a correlation, it's just because the sample is too small. The conclusions are not certain. So what do we do? So again, there are two things about correlation. Number one is that we have the correlation coefficient, which we calculated from a sample. So that's a sample statistic. If that thing is significantly different from 0, if it's closer to 1 or -1, then we can think about maybe there's a correlation. But then we also have a sample size. And that is an important thing too. So if the sample size is small, the correlation might be just coincidental. If the sample size is large, that plays a role. So we have to have both in the game. All right. So for the story today, we're talking about the test of significance correlation. When the correlation is significant, we need a couple of conditions. Actually, about 3 of them, but I'll just point out 2 that are very important. Number 1 is that the sample points are at random. That means that they should not be dependent in any way. So for example, when we have those group of students we had last time, 10 of them, when you have the first students and you have the quiz number 1, quiz number 2, the second student, quiz number 1, quiz number 2, the third student, quiz number 1, quiz number 2, blah, 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 the 10th students, quiz number 1, quiz number 2. Those students should not be connected, meaning that the relation between them ought to be random. So there's like a random students. They are not going to be like two people that studied together or anything like that. There might be some connection between one and another. So that's the condition. So if we don't have sample points random, then we can't do that what we're going to be doing today. That's one condition. Another condition is whenever you have an X fixed. So for example, if I only consider the students whose first quiz was at a score 10, then I will have those students and I will have their second quiz score. That second quiz score of all of those students ought to be distributed normally, which means in the bell-shaped form. And it has to have the same variation. So if I take the students with the score 10 and I have the students with the score 15, again, their second score should be distributed normally with the same variation. So that's a second condition. So we need to have these two conditions, and the vice versa also. If I fix the second score, that all of the students they have that second score and are looking at that first score, those scores have to be distributed normally. Let's say we have those two conditions. So routinely we will assume we have them, and generally that is the case often. It's a little bit harder to expect the same variation, but it generally is the case that that those conditions would hold. What happens then is that this thing here is a random variable. And we know exactly what this random variable is. By the way, I could have written this. Okay, what do we have here? Correlation coefficient, the sample size minus 2. That's degrees of freedom for both samples, because the first sample you have to subtract 1 degree of freedom, and the second sample you have to subtract 1 degree of freedom. So you have an X part of the sample and Y part of the sample, so you're subtracting 2 degrees of freedom. Right? So this is degrees of freedom of the paired data. Again, you lose you lose 1 for X, you lose another 1 for Y, so you have n minus 2. And the number 1, and this is science called coefficient of determination, but it's just a square of R, which is a coefficient of correlation. Again, since from sample to sample, this thing will be different. You take one sample, you get one correlation coefficient, take another sample, another correlation coefficient, take a third sample, there'll be probably a third one, and so on. So this is basically a random variable. It changes from sample to sample. So we're going to label it with the uppercase R, which is how we usually denote random variable, uppercase label. Okay, so now this is a random variable. Okay, what is random here is R, because it will differ from sample to sample. In one sample is going to be one thing, another sample is going to be another thing. What we know about this thing here, this is a number. For one sample, is going to be one particular number. It's going to be statistical that sample. For another sample, is going to be another number. Will be statistical that other sample, and on you go. But we know that this, in general, from sample to sample, is a student T random variable with n minus 2 degrees of freedom. And that's very important, because then we know that this ought to respect that student T curve with n minus 2 degrees of freedom. And we know the distribution of that kind of curve, right? So again, if we have the sample points or the students, like we are talking about that particular pair data we had last time, independent from each other. And whenever you fix the first quiz score and all of the second quiz scores for that particular first quiz score are distributed normally, and vice versa, when you fix the second quiz score, the first quiz score are distributed normally, then this is going to be a student t-random variable with n minus 2 degrees of freedom. So in our story about those students, that will be 10 minus 2, 8 degrees of freedom. Okay? So that's what I'm gonna have to remember this. Now, what is the test? Well, for one thing, you're gonna have a level of significance like we have for every test we were doing in the past. Again, the level of significance is what are you going to allow as the maximum possible probability of making a type 1 error, as in rejecting the true null hypothesis. Okay, what is the null hypothesis here? Well, the null hypothesis in tests of significance will be hypothesis that there is no correlation in population. Okay? Now that's a lengthy sentence to write. So, no correlation in the population. What does that mean? Well, it means that there will be no relation between X and Y. So in case of those students, or that I have 10 of them in my sample, in the population, I would say the quiz number 1 and quiz number 2 are not rated. I can't say, you know, if the quiz number 1 is better, the quiz number 2 is going to be better. Or if the quiz number 1 is better, the quiz number 2 is going to be worse. I can't say nothing about it. Okay? Now, I can write it this way, but I can also write it in algebraic sense, in algebraic way. Okay? So we have something that we call population correlation coefficient. Correlation coefficient in population. This is a Greek letter R. So I'm not writing a Latin character R that we use in Anglo-Saxon script. It's a Latin script, not an Anglo-Saxon script. It's a Latin character. We use a Greek character R. Greek R, we usually call that, it's like any other Greek character that we use. I think we use that only for fraternity and sororities nowadays. But this would usually be called rho, as in this. Okay? So why am I using the Greek character? Why am I not using just simply R, the R of the population? Well, because this is a single number. It's not a variable. There is only one population, and that population has a correlation or not. But in either case, it's a correlation coefficient. So you can calculate the same way we were calculating for the sample, only that you would calculate for the whole population. Generally, you won't know this. So whatever this is, it's a fixed number. And if it's 0, that means that you don't have a correlation in a population. If it isn't 0, then it means you have a correlation in the population. Now, the correlation can be positive. It could also be negative. So when you say there is no correlation in the population, meaning that knowing the first quiz score, I have no idea what the second quiz score is going to be, then I would say correlation in the population is 0. No correlation in the population. That's a short way of doing it. Okay, now what's the alternative hypothesis? Well, alternative hypothesis is one of the three. Like usually, we have, there is a correlation in the population. So which means you're simply rejecting this. So you are saying, no, this would mean there is no correlation in the population. This would mean there is a correlation in the population. But also your sample might tell you something. It might tell you there is a positive correlation, or it could tell you there is a negative correlation. So you could use positive correlation. That's a right tail test. So you're going to say rho, the correlation in the population, correlation coefficient of the population is positive. If your sample tells you that story we had about the quiz, that would be indication that we have a positive correlation. Meaning, when I have a better quiz number 1, I will likely to have better quiz number 2. Okay. Also, your sample might tell you exactly the opposite. It might tell you I actually have a negative correlation. Negative correlation in the population. That's the story about the police officers and muggings. Right? That the more police officers on duty, the lower number of muggings. So that means that your sample is giving you indication. You have your sample, which is an evidence that you have less muggings if you have more police officers on duty. And that means that correlation in the population is negative, less than 0. Okay? You're going to use one of the 3. You're going to use this one if you want to have unbiased approach, or if you have information from a sample that tells you positive, then you're going to use this. Negative correlation, then use this. So again, 2-tail test, right tail test, left tail test. Okay? Then you're going to have a test value, or as we call it, test statistic. And that's going to be exactly what I stated before. It's going to be this number. Because that is a student T, an instance. You're going to have one sample, so you're going to have one out, right? But this instance is a T value. It's going to be an instance of T random variable, student T random variable with n minus 2 degrees of freedom. Whatever the size of sample is, subtract 2, and that's going to be degrees of freedom of this distribution. So this is one particular number. You're going to have one particular number, but it will be distributed as a student T random variable with n minus 2 degrees of freedom. Again, remember this is n minus 2 now. So the n is the number of pairs you have, but because you have x and you have x and then you have y, you're going to lose 1 for each variable. So it's going to be n minus 2, not n minus 1. The n is going to be the number of pairs. The data is paired. So it's going to be the number of pairs. Okay? And then you have a rejection criterion, just like we had in the past. Rejection criterion will be when the test value is in the tails. If you have right tail in the right tail, if you have left tail test in the left tail, or if you don't want to have any bias in your alternative, then you're going to have a T value in one of the 2 tails. Okay, so that's the story. This is the setup. This is the test value, and then you have a rejection criterion, so which means you're going to have to make some kind of a sketch that you know what you're dealing with. And again, so this is the assumption that there is no correlation. This is the assumption there is a correlation. This is the assumption there is a positive correlation. This is the assumption there is a negative correlation, all about population. Okay, this is a test value that is a student T random variable with n minus 2 degrees of freedom, given the condition I stated in the beginning. And rejection criterion is a criterion when it's satisfied, then this is rejected, or whatever is that you have as an alternative, one of those 3, not all 3, right, as usual. Then you're going to accept this one if you have a rejection criterion. If rejection criterion is not met, that will simply mean that you do not have enough evidence from your sample to claim that this is not true. Which means you say, I don't have enough evidence to claim correlation in the population. So this might as well be true. I don't know, but I am not going to reject it. Okay? So let me give you one example. The example we did last time, it's in this lecture quiz example. So that story we had from the last time, you have the bunch of students taking the 10 students taking the quiz number 1, taking the quiz number 2, and I have calculated the R there. It was like 0.89. So I would assume, if I want to test, is there a significant correlation between the quiz number 1 and quiz number 2 scores? Then I would use the positive correlation alternative. So again, the null hypothesis, the quiz number 1 doesn't matter for the quiz number 2, or the quiz number 2 doesn't matter for quiz number 1. They are every which way. It doesn't matter what you score on quiz number 1. I can't tell you anything about the quiz number 2. I don't expect better or worse on anything at all. All right? But our sample tells us that the people that score better on quiz number 1 score better on quiz number 2. We had that in the sample. We had the R of the sample to be 0.89. So the alternative ought to be, there is a positive correlation. When you get a better score number 1, the quiz number 1, you're going to have a better score in the quiz number 2. Okay? Now we can calculate this. How do we calculate it? We just plug in the value. So the R that we calculated last time is 0.892. Okay? Then we have the N is 10. You have 10 students. And down there we have 1 minus, and you can make a square of that. It's going to be 0.892 squared. And now work your calculator, right? You have to be careful. So this is 8. This is, you got to square it. I got, when I squared it, I got 7.96. Oh, excuse me, 0.796. And then you divide whatever that is, and then you take a radical and you multiply 8.92. And what do we have? I got 5.586. That is the test value. Okay. Now, what is our conclusion? Well, since we do have the right tail test, we are going to be looking for the t random variable, sort of a bell curve. It's not a normal random variable, but it's a student t random variable with 8 degrees of freedom. I have to decide, I do have to decide whether I have %5 significance or something else. So in general, if I don't have any better idea, I always use 5% significance. So when you are calculating confidence interval, you usually use 95% confidence. When you're doing a test, if you don't have any better idea, use 5% significance. So I'm going to use 5% significance. Now 5% significance, I am looking for this part to have the 5% of the total area. I made it much bigger here than, but this is just a sketch, so it doesn't matter. And I need now this number here. So I need the critical value. That is called critical value. Critical value where the tail of 5% starts. So this is 95%, this is 5%. Okay? What do you have to do? T-tables. In T-tables, you'll be looking for, pull the T-tables. Hope you have a T-tables either in the textbook or the ones that you have that I put in the handouts. In the T tables, you'll be looking for 8 degrees of freedom. 8 degrees of freedom. 10 minus 2. And you'll be looking for probability in one tail to be 5%. And I found that in the table I have the probability in one tail to be 5% is happening in starting with a critical value 1.860. So this is 1.860. So again, check the tables and you'll find it in the tables. See that? 8 degrees of freedom. On the top, you see the 5% in one tail, and that what I found is 1.860. Those are the T tables. Okay, so you will have the T tables. You can find it yourself. Okay, so I have that. I disconnected some electricity here. All right. So where is my test value? Well, that's way over there in the tail, right? We're talking about 1.860. This is 5.586. So this is 3 times that way. So this is undoubtedly in the tail, which means this could be rejected. So I have the rejection criteria. I met the rejection criterion. The test value is in the tail, and that means this is rejected. So the null assumption that there is no correlation in the population is rejected, and the alternative assumption is accepted, meaning that there is a positive significant correlation in the population. That's why it's called test of significance. There is a significant positive correlation in the population. If you want to be even more precise, you're going to say there is statistically significant correlation, which we already kind of know. That's when you have a better score on the first quiz, there will be better score on the second quiz. That's what it means, right? And our test confirms that very strongly, because we just need to pass 1.860, and we went way over that, and we have it. Okay. So in the paper, in the paper that is a lecture paper, there you will find that I was actually using in the paper the unequal here. So I was using a two-tail. So you might want to read that. But the conclusion was still the same. So I was using a two-tail alternative hypothesis, and conclusion was also the same. I rejected the null hypothesis. Okay. Now we have another example. When I was collecting the data about the students attending my calculus class. And so I was assuming that might be some relation between the attendance and the success on the final exam. So the assumption was that the idea was that the people that are attending more regularly are going to have better final exam. So I had this table. So again, this is in the lecture. That's example number one in the lecture, so you can find it out. I had that one student had missed the class once, and he's got a 77 on the final. Another student missed the class twice, and he's got 65. on the final. Another student never missed any class, so this is absence actually, and he's got a 59. Kind of disappointing, right? He never missed the class, but then he failed the final. But then I have another student missed 4 times, he got a D. And I have another student that never missed the class and he got an A on the final. And then I get another student that missed class once and got an A82B on final. And I have another student that missed class twice. He's got 51 on the final, failed. And I got a student that missed class twice and somehow squeaked through with a D. Okay, so I have a bunch of students here, 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. And this is the absences. This is the percentage on the final. Okay, so now the question is there a relation between the final and the number of absences, or the number of absences and the final test score? You could immediately say, oh, of course there is a relation. No, but we don't know that. Okay, so in the science you don't make conclusions based on your feeling about it. You are going to do the test here. First of all, in the lecture, so you're going to have to read the lecture. In the lecture, I calculate the R here, right? So I made a whole table: X, Y, XY, X squared, Y squared, and then I use the formula 1,3, that formula with lots of radicals and summations, and I ended up that I got the R being approximately negative 0.4071. It's kind of weak R, but it's what you could expect. It's negative, so which means the more absences, the lower score. The bigger X, the lower Y. That makes sense. It's just not that much. I mean, it's not really close to -1. It's actually closer to 0 than to -1. So the question, this is a good question here. Is there a significant correlation? When the people are making lots of absences, would you expect them to have a bad final? So let's test it. So this is my test here. The assumption is that there is no correlation, no assumption, right? But I really want to make a conclusion that there is a correlation. So I'm actually looking for the alternative to be accepted. And the alternative that I'm going to use here, I'm going to use now two-tail alternative. I could use that there is a negative correlation, because that's what I'm getting here from the sample. Okay? But I'm just going to use a two-tail alternative. That's never a mistake, right? I don't want to have any bias. The sample says you could have a bias. You could say there's a negative correlation, because you're definitely not going to have an evidence for positive correlation, because the sample gives you some evidence, and that evidence seems to be for negative correlation. But I'm not going to use that. I'm just going to use two-tail alternative. Okay? Now the test value is again the same story. So now you have to calculate the test value, which is going to be R times the radical. On the top you have 6, 8. Number of pairs is 8, minus 2. On the bottom you have 1 minus negative 0.4071, and you have to square it. So one way or the other, you're going to come up with some number here. So my calculation of this expression shows up that I get negative 1 point something small. Like this. Okay? You can check this out. It's just a calculator business. It's not a big deal to do that. It takes a grocery calculator. Okay. Now, rejection criterion. I'm going to use 5%. So again, significance level of 5% is the kind of customary thing to do, colloquially acceptable everywhere. If you don't have anything better to think about it, and you can use a 5%. Now, if you want to relax it, you can use 10%. If you want to have something a little more precise, you want to use 1% or something like that. But now I'm going to just simply use 5%. Okay, 5%. So the level of significance of 5%, and we are looking for the T curve, where I'm going to have 6 degrees of freedom because the sample size, the number of pairs, is 8. And I'm going to lose 1 for each variable, 1 for x, 1 for y. So I'm going to have 6 degrees of freedom here. 6 degrees of freedom for this distribution here. And I'm looking for a 2 tails combine 5%. So I need to have this tail here of 2.5% and this tail here of 2.5%. Combine 5%. What I need is this critical value here. This one here is going to be negative, and this critical value is going to be positive something. Right? 0 is in the middle. 2 critical values. 2 critical values. Okay? Because you have 2 tails. Okay. Again, you're going to be looking at the T tables. So this time you're looking for 2 tail, 6 degrees of freedom. Okay? So I'm looking for 2 tails that have 6 degrees of freedom and 5%. I think I found the value. $2.447. One of them is positive, one of them is negative. All right? Let me show you that again. The monitor comes on. You can see. So again, 6 degrees of freedom. These are T tables. On the top, you can see that I'm selecting 5% in 2 tails. And that's the number I'm getting in from the table, 2.447. The table, of course, have only positive values. But you got to remember that you are dealing with the 2 tails. And having 2 tails will imply negative 2.447 and the other one positive 2.477. Oh, excuse me, 447. Okay, so I have this test value, and it isn't in the tail. It's actually here. Okay? It's not in this tail, and it's certainly not in this tail. which means that our conclusion here must be we don't have enough evidence to reject this null hypothesis. We cannot claim that there is a correlation. Your conclusion should be, we don't have enough statistical evidence to claim statistically significant correlation between the absences and the final test scores in calculus. Now you can say, oh, how could that possibly be? All right? Because we know from the practice and from practical situation that the people that are missing lots of classes are going to have lousy scores on the finals. But what's the problem here? Well, the problem is not an R. The problem is the size of the sample. I have 8 students only. So basically, what is this? The conclusion telling you, my friend, you don't have enough students here to make that kind of leap into conclusion. So if you really believe that there is a correlation between the absences and the final test score in calculus, you need to go for a bigger sample. And if you have a bigger sample, maybe you'll get that. But with this kind of sample and with this relatively weak R, because it's not close to -1, you are not going to be able to conclude that. You cannot reject this one, which means you cannot accept this one. You cannot say that there is a correlation. And I would even want to claim more. I would like to claim that there is a negative correlation, but I can't even claim that there is a correlation because my rejection criterion is not met. I don't have the test value in the tail. It's not in the tail. It's not in the tails. I use the two-tail alternative. Okay? So again, this is the kind of the things we do if we are going to make conclusions about the correlation between two random variables. Now, in this particular case, random variable absences from the class lectures and the random variable score on the final exam. Now, this topic, testing significance of correlation, will not be included on your test on Monday. On Monday, you have a test on Connect Math. We'll do selection from the homework problems, and hopefully we're doing those homework problems. And the test will be based on the previous topics up to the lecture number 11. This is lecture number 12. So we are not going to have this. So you're going to be asked to calculate the correlation coefficient, but you will not be asked to test the significance of correlation. However, of course, this is going to be on the test number 3. So in the test number 3, I'm going to ask you about the how do you decide whether you have statistically significant correlation between the two variables. And again, you use this so-called t-test of significance. So here we don't have a z-test. It's only t-test. Okay? You're going to remember also this is the test value. We have never met this test value before. That's a different test value we have. And you also need to remember that this is a student t test value. Size of the sample in terms of pairs, how many pairs? -2. So you have 8 pairs, -2, 6 degrees of freedom, 10 pairs, -2, 8 degrees of freedom, 50 pairs, 48 degrees of freedom, and so on. Okay? So I have the a little more writing on those tests here. I want to read this in the lecture. The one thing I want to spend time about is to say, what is this guy? Okay, so I already mentioned that's a square of R. And we call that coefficient of determination. So we're referring to R as a correlation coefficient. Correlation coefficient. And when you square that, we call that coefficient of determination. This has a theoretical value. We are not going into explanation of this theoretical value, but you're going to have to remember that this is actually determining the relation between the variations. When you have two variables, you have an x and y, and you have a sample, this guy will tell you how related these two guys are. So we talk about it already, for second lecture. So if there is a relation between x and y, this guy will tell you something about it. This guy will tell you about the relation between the variances of these two guys. That's kind of important thing to know too. So, for example, this one have lots of variations. So now, how is this connected with variation of y? Or this one might have a little variation. So now you ask a question: how is that? What kind of impact is little variation here going to have on the variation of y? So there might be a relation. So if there is a relation between x and y, it's likely that you're going to have a relation between their variation also. And that variation is expressed also, the relation between the variations is expressed also in terms of percentage. So, for example, if the correlation coefficient is negative 0.8, so which means that whenever the x is bigger, the y is smaller. Whenever the x is smaller, the y is bigger. They go in a different direction. You have a negative correlation. I didn't say it's significant, because that has to be determined by the test of significance. You need to also take into consideration what is the size of the sample. Now, if you square the 0.8 negative, you're going to have 0.64. So now you can say, if this is a relation between the x and y, 64% is the relation between x and y variations. In other words, I should say that whatever is the variation here, it will have a 64% impact or relation with the variation here. And there are, what else is there? 36%. There is a 36%, there's something else is in the game too. So if you start changing here variation, if you make it bigger, this one will change to the scale of 64%. Meaning, if you change significant to that, 64% of that significant change you're going to make here is going to be seen in the change of variation of y. But there are other 36% also, something else in the game. So that's the meaning of the coefficient of determination. Now there is a much longer story into that, and there's a much more sophisticated explanation here, which is something we would be doing in the business of statistics that would be based on calculus. And we are not going to be doing that, so you do not have to worry about it, okay? What we usually require whenever we are testing the significance of correlation, we usually require that sample size is at least 10. So that story about the students I have with 8 students only, about the absence from the classes and relations with the score on the final exam, that would be something we would not be even testing, because it's just simply not enough for any test. So we usually require to have test when we have at least 10 pairs. Right? You're gonna remember that if you do the test, you will need to have at least a sample size 10. More likely, you would want to have something much bigger, though. Okay, so that's my story for today. I want you to prepare yourself for the exam on Monday, because that's going to be those lectures we have. The I think it was the number 5, 6, 7. No, I don't know exactly, but up to number 11. Whatever was done after the test number 1. And let me check this out. Actually, I can take a look at that. So we have the lecture number 7, lecture number 8, number 9, and number 10, and number 11. So those are the lectures that are relevant to the test number 2. And this test of significance we were doing today is just a filler between the last lecture we have for the test number 2 and the test number 2. But this, of course, is going to be the topic that is going to be on the test number 3. Test of significance or correlation, right? Okay, now I'm going to stop the stream. You can watch this over again if you wish, and I'll see you on Monday. Well, actually, I won't see you. I will have a Zoom conference meeting if you want to check it out, and I'll just simply post a test for you on Connect Math. So on Monday during the class time, you just go to Connect Math and work on the test. The test will be a lot more stringent than your homework, so you're not going to have an access to help stuff that you have for the homework, and you will have the 2 tries on every problem. So you're not going to be able to go, I don't know, unlimited number of times to the problem if you cannot answer that correctly first, second, or third time. You're going to have to make it in 2 tries. So if you make a mistake, the second time you put a number in, you better have it right, because you're not going to have a third chance to correct that. It's going to be similar like we have in the makeup quiz. Okay? And I'll give you one extra question. It's an extra credit question. I already promised that's going to be one of those testing or the population mean thing that we have in the lecture number 9. So, okay, prepare yourself. Make sure you work on the homeworks. The homework will prepare you for the test number 2, because the test will be made out of the homework problems with one extra problem that we have in the lecture number 9 on those 2 or 3 problems that are at the end. Okay, I'm going to stop the stream, and I'll see you Monday.